In this video, we are going to investigate how orbital overlap and quantum mechanics can help us understand a little bit more the picture of covalent bonding and how it's going to lead to a better representation of how we can view chemical bonding. So we talked about VSEPR theory, and it does a great job at predicting shapes, but very little information is given about the actual bonding. So a theory called valence bond theory was developed. And what valence bond theory tells us is that the electrons are moving around in orbitals. The better the orbitals overlap, the better the sharing, and the stronger the bond. So this bond strength is going to be based on orbital overlap. Orbital overlap is going to depend on two main factors. Number one, the shape of the orbital, or the shape of the orbitals interacting. Another word we'll use for orbital interactions and shape is called symmetry. The second is the energy difference in the orbitals that interact. And this is going to be proportional to the difference in electronegativity. So if the orbitals have a shape that allow them to interact well, we're going to have strong overlap. And if the energy difference is very, very minimal, they're going to interact well. Okay? If orbitals have a much different energy, they're not going to interact well. So before we look into how these orbitals interact or how they could potentially form something called hybrid orbitals, let's go back to a wave-like picture of how the orbitals are. And remember, we said that in a 2p orbital, we have one angular node. And that angular node is going to be based on the fact that the electron behaves as a wave. So if we have a wave right here, we can represent that wave as a positive and a negative. There's a positive and a negative portion of the wave. Okay? For that wave, at this point right here, the amplitude is going to be equal to 0. Okay? When we represent our orbital, in the same fashion, we have a positive and a negative lobe, and we have a node right here in the middle where the probability is going to equal 0. Sometimes the orbital is represented shaded like this, showing that the wave function changes sign from positive to negative. So here's our function of our wave with a positive amplitude and a negative amplitude and an amplitude of 0. Our probability density function is going to be the square of this amplitude. So basically, when we square this term, we're going to get something that looks like this. Okay? Because when we square a negative number, it's going to be a positive number. And this relates to the picture that we see in the book where the orbitals aren't shaded. Okay? We still have the node here in the center where the amplitude is going to be 0, where the probability of finding the electron is going to be 0. And this is all based upon the wave-like nature of this electron. Okay? We also know when we talk about waves that we can have constructive and destructive interference. Okay? So let's look at kind of a graphical representation of a few waves. We're going to have one wave that we can represent like this, and another like this. We have a positive portion of the wave function and a negative portion of the wave function. If I add these two waves together, what's going to result is something that looks like this, where the amplitude of that wave is going to be twice as large when we add them together. If, on the other hand, we look at waves that are added together, and I add one wave that looks like this, and add that to a wave that looks like this, their amplitudes are going to cancel out. So when electrons are traveling through space, behaving as these wave-like species, they could either have constructive interference or destructive interference. And when we look at how bonds form, when we have constructive interference, we're going to have two orbitals come together with the same phase. When this happens and we add these two orbitals together, we get a resulting orbital that looks something like this. Okay, this right here indicates that we have a strong bonding interaction. If, on the other hand, we have two orbitals that come together of opposite phase, where our interaction here is something that has two waves that destructively interfere, we're going to get something that looks kind of like this, with no electron density in the center section. Okay, so we can kind of characterize this. On the left-hand side, we have a bonding interaction, and over here on the right-hand side, we're going to have an anti-bonding interaction. And this is going to help us piece together something called a molecular orbital diagram, which we're going to get to in the next couple sections. But before we go ahead with that, we need to talk about something called hybrid orbitals. Because these waves, if we have an s orbital and a p orbital, when we mix them together, the function is going to be a little bit different, and we can get different types of shapes. So that's going to be the topic of the next video.